At the end of the 19th century, the world stood on the edge of an impossible idea: flying. For thousands of years, the sky had belonged only to birds, clouds, and storms. Humans could look up, but never stay. Inventors tried anyway. They built wings from wood and fabric. They jumped from hillsides. They glided briefly through open air, and for a moment, it worked. But those moments never ended gently. They ended suddenly, violently, without mercy. Early aircraft did not fail because they lacked power. They failed because they lacked control. Most early pioneers believed flight was a problem of strength. If the aircraft fell, they added more engine. If it stalled, they added more thrust. If it broke apart, they blamed weak materials. They believed the sky could be conquered by force, but the sky does not respond to force. It responds to balance. Power determines whether an aircraft can leave the ground. It does not determine whether it can survive once airborne. Because the moment an aircraft enters the sky, it enters an unstable world. Air moves unevenly. Forces shift constantly. Gravity never relaxes its grip. The consequences are immediate. That loss of balance has a name: roll. Pitch lifts the nose up or pushes it down. Yaw turns the aircraft left or right. Humans understand both instinctively, but roll is different. Roll arrives quietly. There is no sudden drop, no violent pull. Just a silent difference in lift between two wings. One wing rises, the other falls. And once roll begins, it accelerates. By the time early pilots realized what was happening, their aircraft was already unrecoverable. This is why so many early flights ended the same way: a calm launch, a brief glide. Flying had been achieved. Controlled flight had not. Air is never perfectly equal. One wing always experiences slightly different conditions: a gust, a pressure change. A tiny difference in angle at first, the imbalance is small. But roll feeds itself. As one wing dips, it moves faster through the air, creating more lift. The opposite wing slows. The imbalance grows. This feedback loop is ruthless. Early aircraft had no way to interrupt it. Pilots were not flying the machine. They were enduring it. And there was another hidden problem. The human body cannot sense roll quickly enough. Our inner ears evolved for life on solid ground, not for subtle aerodynamic imbalance. By the time the brain reacted, the aircraft was already unstable. The solution would not come from bravery or strength or speed. It would come from engineering control. Wilbur and Orville Wright approached flight differently. They did not begin with engines. They did not chase speed records. They asked a more dangerous question: how does a pilot control an unstable machine in real time? they understood something revolutionary. An airplane is never naturally safe. It must be actively balanced every second it is airborne. Without roll control, no amount of power would ever matter. In our previous videos, we broke it down. So, if you truly want to understand how modern aircraft learned to fly, go back, watch the earlier chapters. The links are in the description below, because the sky never reveals everything at once. The Wright brothers turned biology into mechanics. They built wings that could flex. Using cables connected to the pilot's body, they twisted the wings in opposite directions. Lift increased on one side. Lift decreased on the other. For the first time in history, a human could command roll. This system was called wing warping. It was crude, fragile, mechanically demanding. But it worked. And in working, it proved the most important truth of flight. Control, not power, was the missing link. As aircraft evolved, forces increased, planes flew faster, wings grew stiffer. Twisting entire wings placed enormous stress on the structure. At higher speeds, wing warping became dangerous. The physics was correct, but the method could not survive progress. Engineers needed a better way to redistribute lift. The solution was elegant. Instead of twisting the whole wing, engineers moved only a small section of it. Hinged surfaces near the wingtips could increase or decrease lift on command. These surfaces were called ailerons. One moves up, the other moves down. Lift shifts. The aircraft rolls. The idea had not changed. Only the execution had improved. Ailerons introduced new challenges. The downward aileron increased drag, causing the aircraft to yaw opposite the turn. This problem, called adverse yaw, forced engineers to refine control even further. Rudders were coordinated, systems evolved, but the core principle remained untouched. Roll is controlled by redistributing lift. Today's aircraft are filled with computers. They interpret pilot input. They limit extremes. They protect the structure, but computers do not replace physics. They manage it. When a modern jet banks smoothly across the sky, it obeys the same rule discovered over a century ago. One wing lifts more, the other lifts less. That difference still decides everything. Materials evolve, engines advance, avionics transform. But physics does not age. The principles of balance remain eternal. In aviation, control will always matter more than power. Human flight did not become possible because engines grew stronger. It became possible because engineers learned how to control instability. The Wright brothers did not conquer the sky with speed. They conquered it with understanding. And more than 120 years later, every airplane still trusts that same idea. Because in the sky, control is everything.